Welcome. I will be presenting here our work on food portion estimation on spoons, conducted at VipLab under the supervision of Professor Yuhao Chen and Professor Alexander Wong. My name is Chris Czarnecki, and I have co-authored this work alongside the brilliant Aryam Sharma. The title of the paper is How Much You Ate: Food Portion Estimation on Spoons. Big thank you to all the authors of the paper for contributing to our work. Let's start by providing some background. Traditional ways of portion estimation range from pre-meal and post-meal photo captures to wearable tracking devices. For example, a tracking device by Zhao measures vitamin C intake using a lithium perchlorate and gold-doped electrochemical sensor. Vitamin intake can be then estimated from sweat, urine, or other bodily fluids. This is fine if you're a healthy individual, but what about children or the elderly aging at home? Vision-based nutritional content estimation is non-trivial. In many perception tasks pertaining to food, humans rely on multimodal information to decide whether food is safe to consume, whether it is nutritious, and whether it tastes good. Vision is a critical component of it, but our eyes lack the ability to accurately estimate nutritional content. Some studies show that 24-hour recall-based nutritional tracking methods might be incredibly inaccurate, with estimation errors reaching 400%. The question is, can computer vision-based solutions do a better job of nutritional content estimation than a human? Focusing predominantly on individuals aging at home, we envisioned a solution which would be minimally invasive and which would require minimum active input from the user for accurate nutritional content estimation. We have agreed that a tracking system based on a static camera would be a good solution. We would like it to fulfill two major criteria: a set it and forget it approach, so once the camera is set in place, the system would work with almost no direct user interaction, and also best interface is no interface approach. A fully automated system abstracts all complexity away from the user. The specific challenge our work is addressing is accurate volumetric estimation of food items, which could be then adapted to nutritional content estimation pipelines. In this example, you see a dish where submerged dish components make it hard for a vision-based system to differentiate between the liquid and the solid parts. Even to a human eye, it is much more straightforward to determine that the dish in question is baked beans when a smaller portion on a utensil is presented. Thus, we propose to conduct volumetric estimation of dishes on spoons. Dishes like stews and soups are prevalent in many cuisines. They tend to also be easier for elderly people to ingest, as they typically require less chewing. Here are the strengths of the concept that we propose. First, we fulfill our user-friendliness requirements. We fulfill the set it and forget it approach and the best interface is no interface approach. We can detect submerged bits of foods, and we can also recognize partially finished meals. We envision a stationary camera placed in one position in front of the subject eating, and we use it to monitor the food on the utensil. For our first trial, we processed frames in a video capture of a subject eating using a combination of grounding dyno and the SUM-HQ model. With this approach, we have achieved mean absolute percentage error between 160.6% and 831%. The prompts used for segmentation were plainly face, spoon, and food. In this slide, you can see an example of a misclassification where, for a particular frame, the subject is misclassified as food. We have considered three important research questions. When do we start tracking? How do we handle inconsistent predictions frame to frame? And how do we approximate volume? For the first question, we have to consider that people usually introduce food in video captures. They do not necessarily start eating right away. For the second question, temporal inconsistency when processing independent frames often leads to poor segmentation results. For the third one, what method of volume approximation from monocular view camera should we adopt? Which of the methods might be the most accurate? The solution we propose starts with a video capture. We then investigate independent frame processing and video object segmentation. Then we apply our custom keyframe detection algorithm. Finally, when the utensil and food instance mask is extracted, we apply three different volume approximation methods using parametric shapes, thus obtaining an estimated volume. Our keyframe detection algorithm is a critical part of the pipeline. We rely on distance calculations between centroids of the utensil and the food instance to decide when to start tracking the food on the utensil. We then select the pair of segmentation masks of the utensil and food instance that is the closest to the subject's face. However, computing centroids on segmentation masks that are misclassified significantly increases the error. Therefore, we need to come up with a way of rejecting unreasonable segmentation masks. We leverage a heuristic algorithm for filtering out frames with spurious segmentations. We ignore predictions for instances with volumes larger than 25 milliliters. We also maintain a running mean of good predictions until we receive a consecutive sequence of 5 bad predictions, at which point we stop updating the running mean until the detected volume is within the expected bounds again for any of the subsequent frames. Let's discuss our results. The best method was ellipsoid approximation without video object segmentation and with the filter applied, marginally outperforming ellipsoid approximation with XMEM and with filtering on. We can also notice that for scenarios where the filtering algorithm is not applied, VOS pipeline performs much better, likely due to the inclusion of temporal information. Segmentation mean intersection over union was larger for independent frame processing, which indicates greater accuracy in segmentation. We also present results for the best frame, single frame for which MAP or MAE was the lowest. To summarize, we have proposed an end-to-end volumetric estimation pipeline for food present on spoon. Our approach is non-invasive and requires minimal interaction from the user to remain effective. Our approach solves the problem of tracking, particularly partially finished portions and hard-to-estimate meals such as soups and stews with submerged solid parts. In the future, we would like to extend our method to other utensils such as chopsticks. We also recognize that very often our hands serve as utensils. This is prevalent in many cuisines of the world and also applies to some typical North American dishes such as burgers. Another issue we would like to address is tracking food types of which segmentation masks would extend well beyond the utensil, for example spaghetti noodles. We are happy to report that our project has received considerable media attention, with one article in New Scientist and one in Sky News. We include QR codes to those articles for your convenience. Thank you for your attention and for your interest in our research. We would like to thank the National Research Council Canada and the Aging in Place program for providing funding for this project. I and Ariam would like to extend heartfelt thank you to Professor Chen and Professor Wong for mentorship over our project.